And next, we have our last talk for today. We have Theodosios. I'm sorry if I'm mispronouncing your name.
Hello, yes, please call me Theo.
Perfect. So Theo is going to talk about a non-conforming hydroelastic finite element of ice shell flexure under long wave extension. Okay, go ahead.
Yes, I don't know if you can see my screen now. There should be a PDF file.
Yes, we can see. Perfect.
So, first of all, let me thank the organizing committee for this very interesting workshop, and good afternoon to everyone from Birmingham, UK. So I will briefly talk about the oceanic wave impact on ice shelves, and then discuss hydroelastic flexure equations for specific type of models and the resonating ice shelf problem. I will present variational forms and the finite element discretization using non-conforming finite elements for modal analysis, but also for the scattering and radiation problem, and then discuss a very rough model of the large and sea ice shelf and some conclusions. This work I initiated while I was in Brunel University in London about maybe 5-6 years ago. And I used to collaborate with the team from the School of Naval Architecture and Marine Engineering from NTUA in Athens. So I will skip the basics. Many researchers have already presented that in the conference, and I'm mostly interested in disintegration due to plate bending and tidal flexure of ice shelves. And the basic regime that I will be examining with respect to the wave forcing is the long period waves. So we are talking about the gray shaded area where we have the shallow water equations with no Coriolis effect, so specific Rossby numbers, and the thin plane approximation due to the span of the ice shelf, the slenderness of it compared to the wavelengths and the thickness and the depth, of course. We can extend, of course, this model going to higher periods towards the right. This would have to include Coriolis effects, but the thin plate approximation should be okay. And then if we go to very small periods or smaller periods, we need, of course, the full Airy wave theory, and then moderately thin plates like the Reisner-Middling model, or even full elasticity theory. So the central regime, infragravity waves, very long period swells, 6 is the area of interest for this study. There are numerous studies on the stability and disintegration of ice shelves. I have included here some of them: Brominsky, Squire and Williams, Sergienko, Holsworth, Atman and al. And of course, there are numerous studies. We have also seen in this workshop several by Squire, Sergienko, Mailan et al., Raman and al., of course. And there are many interesting phenomena with respect to hydroelastic flexure under log wave excitation of Antarctic ice shelves, the major Antarctic ice shelves, the resonance of which have even been associated in some models to localized atmospheric waves. So the oscillating ice shelves drove the waves in the atmosphere. I don't know if this is the actual explanation. It's very interesting one, though. My assumptions here then will be that the fluid motion is irrotational and governed by the linear shallow water equations. The ice shelf is slender, so yes, we have a thickness in the order of hundreds of meters, but the span is enormous. It is elastic, solid, and subject to the Kirchhoff-Love assumptions for plate bending. And the grounding line, so the line where the ice shelf expands from the coast to the sea, is modeled as a hinge zone and is considered to be of small span compared to the overall span of the ice shelf. I will examine the long wave forcing in terms of reflection transmission in the case of a simple 1D model, and as an incident reflected, scattered and radiating problem in the case of 2D. So I will quickly go through the equations. I'm using the linearized shallow water equations, assuming rotationality of the flow in the area of the water where we do not have the ice shelf. We have a D'Alembert type wave equation, very standard. In the ice shelf and sub-ice shelf cavity region, we have the continuity of the mass, so eta denoting the deflection of the ice shelf and phi the velocity potential. And we have the plate deflection where the pressure of the water acts on the lower part of the ice shelf. We take into account the draft according to Archimedes' principle, and we denote as D capital the flexural rigidity and tau the thickness of the ice shelf. We define in the standard way the bending moments, the shear force, the normal bending based on the projection on the outward normal, the twisting moment, including projections on the tangential, and the active shear force. So for the grounding line, we assume that the deflection and rotations of the thin plate representing the ice shelf is zero, and that there is the boundary is impermeable for the water. So we have a Neumann condition for the velocity potential. For the front of the ice shelf exposed to the ocean, we assume zero normal bending moment and active shear force. The effects of membrane stresses, as described previously by Dr. Bennett, they are very important locally, but because of the small level arm of these forces on the thickness compared to the level arm of the span of the ice shelf, will not contribute significantly here in the flexure. In the water at the free edge, we have continuity of the velocity potential outside the ice shelf, and inside it is actually the time derivative in the time domain, and continuity of the flux, again taking into account the variability in the bathymetry due to the ice shelf draft. We transform everything in the frequency domain. So we can also non-dimensionalize. Again, we have seen the similar expression in the previous equation, in the previous presentations as well. And we derive the variational form appropriately testing the plate equation and the continuity equation by shape functions. We see here in the frame the variational form. It has a mass type term, a hydroelastic coupling term multiplied by the imaginary unit. This is not dissipation because of the skew symmetry of the bracket that we have inside an integral. This is actually Hermitian, and we have a stiffness type term including the deformation energy of the plate and the velocity potential terms. So based on that, we can, as a first approximation, close the system with homogeneous conditions, creating three eigenvalue problems, either using Neumann condition for the velocity potential, so no flux inside the ice shelf cavity. This was used by Sergienko in 2013. We can close using a Dirichlet condition for the velocity potential. That means a nodal line at the opening. This is what they typically use in similar situations in harbor engineering, in coastal engineering, and a recent development by Bennett and Mayland, a mixed condition. This third condition is actually closer to the truth, as I like to say, so this is more accurate, the second being very accurate as well for small aperture ratios. So I will focus on the second eigenvalue problem with the zero Dirichlet conditions, and the natural setting for this problem are Sobolev spaces H2 with appropriate homogeneous conditions at the grounding line, and the H1, all of these over the complex numbers with the nodal line at the front gamma F of the ice shelf. And we want to find the eigenfrequencies and eigenforms of the system. So for this system, we know that all the eigenvalues are real. This can be easily proven because of the positive definiteness of the second operator we see, and the fact that the hydroelastic restoring forces are real. And if we have also the frontal line with nodal condition 0, then because of the Friedrich inequality from the second equation, we have strongly elliptic bilinear form. Sorry about that. We solve this problem then as a quadratic eigenvalue problem. We solve it as a reflection problem in 1D. We know the properties of the system. This quadratic eigenvalue problem has been well studied. And we use higher order elements with Hermite interpolation for the plate and Lagrange for the shallow water equations. Here is an application for a transect for the Ross-I self as used by Brominsky also in 2015. And we compare the Dirichlet and Neumann conditions to the local maxima of the response of the I self. The blue line is the energy norm, the red line is a Chebyshev type norm. Always in this example and examples, the local maxima, that means the resonant behavior, coincides with the problem that has the nodal line at the open boundary of the I self. Interestingly enough, if we compare the hydroelastic frequencies or periods equivalently, which are which is the stem diagram, the black stem diagram, to the frequencies or periods of the basin, this is the blue line. In larger periods, we have good correlation with only the basin frequencies, and as we increase, we start to approach the red line, which is the eigenfrequencies of the plate itself, so in vacuum oscillations of the plate. But there is an intermediate regime where the hydroelastic effects are significant. For two-dimensional analysis, we developed a non-conforming hydroelastic element. We need that because of the H2 assumption for the plate deformation. This is very difficult to, in general, although it can be done to achieve in 2 dimensions. So we use non-conforming elements, not in H2, but in H1. We adopted the spect shape functions for the flexure and linear triangle for the water underneath the I self, 4 degrees of freedom per node, deflection, rotations, and the velocity potential. Tested to verify the model with a circular fictitious I self. Half of the circle perimeter is the grounding line, half the free edge. We see here also the mass, stiffness, and hydroelastic coupling global matrix, very well structured. And compare with an analytical, semi-analytical actually solution based on Fourier-Bessel expansions. Good approximation, actually the finite element model converges very fast to the actual solution and is very robust. We have also error estimates for the eigenfrequencies, also for the eigenperiods and the, of course, and the eigenforms. The error reducing with the characteristic size of the mesh square. This error estimate can be easily derived using an added mass type reformulation of the problem, which recasts the analysis to a non-conforming plate with an extra mass because of the effect of the water underneath, and then follows in the analysis of Rolf-Ranacher for non-conforming plate elements. And the results are verified in several examples, so the convergence rate is verified explicitly. Now, for an application, I would like to consider the Larsen C I self, one of the largest I selves. It has a half circular shape, or at least it had until 2017, where there was a major calving event with a very large part of the I self being detached. Here is a very simple approximation of the model using a half circle. The smaller half circle highlighted in blue is actually the part that was detached. Solving with the eigenproblem 2, so zero nodal line, we have several eigenmodes. I started to have a look at the eigenmodes, and I actually tried to figure out if the wave forcing could somehow contribute to the disintegration. Of course, I don't know that. Several mechanisms might have contributed here, and there are several analyses by authors, but the mode 4 looks a prime suspect, as well as mode 5, which produced in about 1/3 of the span high deflections and moments. The number 4 normal moment, number 7 is a twisting moment, actually. Now, these are some movies of the first, 5th and 10th mode. How do they look here, and compared with the 1D model in a transect at the center of the eye shelf. So the analysis can be continued, and similarly to the 1D problem, we can solve this as an incidence reflected and scattered, and I use the term scattered here in general, including also the radiating modes of the oscillating eye shelf. So what I did here is I closed my computational domain using a Sommerfeld condition at the radius r away from the eye shelf, and inside domain omega, I used hydroelastic elements, linear shallow water triangles outside, and applied the Sommerfeld radiation condition on gamma r. And finding the maximum norm of the deflection, even in the 2D, it appears that the eigenvalues are very close to maxima. Of course, now the spectrum is more dense in the 2-dimensional case. There are several modes. There are even modes in certain geometries with algebraic multiplicity, more than one, but geometric, not geometric multiplicity. So I'm trying now to cover some parts of the spectrum and try to find the eigenmodes. For example, I have 3 and 4 in this diagram, trying to locate these forms. And indeed, I did, running this scattering problem. We located at the periods expected mode 3, which has these 3 humps here. We can see in the upper part of this slide, and also mode 4 with a peak and trough here in the lower part. And this is what the simulation looks like for incoming waves. I have here a small movie. This is a frequency in between 2 frequencies, so they are both excited. In the upper part, we see the velocity potential, and in the lower part, a movie of the deflection of the eye shelf, a combination of the 2 modes that we discussed previously. Finally, for some conclusions, I found the non-conforming hydroelastic element to be quite robust. It is relatively easy to implement for hydroelastic flexure, and in my wish list, I would like to have more realistic geometries. We can do that actually now because of the triangle can approximate complex shapes, and maybe go away from the assumption of the half circle for the Larsen CI shelf as a first step. Furthermore, it would be nice to gradually expand the model to go to smaller periods, so we will need Airy wave theory and Reisner-Midlin plates, or even elasticity theory then. And having seen several very interesting and nice presentations, I was wondering if the same model can be, the same element can be used for ice flow simulation under long wave impact. I have included some movies here as well. I intended that for very large floating structures, so the shape is a gamma type domain. We see on the right the velocity, the upper surface elevation by releasing a wave. This is time domain simulation now, and a zoom of the plate deflection as the wave arrives. Thank you very much. I hope I was in time. I try to move quickly in case there are any questions.
Thank you, Theo. Thank you very much. Any questions? We have one question, just a second.
Hi, I have a question. Thanks for the talk. So So the non-conforming element, is it similar to the Morley finite element for fourth order problems?
It is more accurate than the Morley. The Morley has less degrees of freedom, and the Morley assumes continuity of the gradient at the sides, but is not even H1, the Morley.
Okay.
So the spect has more degrees of freedom, so it's more computationally heavy, is an H1 element, but not H2. The Morley, in this case, I have tried, but I believe it doesn't work because of the incompatibility of the spaces between the two equations. So L2 is not enough. I have not completely figured out this problem, but I believe that for the coupling, L2 might not be enough. We need at least H1, even for the plane.
Okay. Another question. So have you considered other methods like DG, discontinuous Galerkin or something like that? Is it applicable for these kinds of problems?
We are currently working on discontinuous Galerkin for the fourth order problem. There are several, let's say, studies regarding that. Discontinuous Galerkin is way more general. So, for example, the spect shape functions probably can be derived as a special case by penalizing appropriately the jumps at the sides in a discontinuous Galerkin set.
So probably, I don't know, maybe it's a little more, would it be more expensive compared to these non-conforming elements? Because DG doesn't involve any sort of like continuity requirement between the elements. So does it involve more?
Correct. Depending on how you program it, it could be very effective. The price you pay for that, the numerical complexity must be preserved. This is a law of the conservation of numerical complexity. The amount of effort that we save in, let's say, setting up specific shape functions, we lose having to introduce the penalty terms. But in general, the discontinuous Galerkin method is more versatile and more robust. However, the spect shape functions are they are considered a legacy now at this point, but they have been well tested, well documented. So it was a natural first step to get the first results with good control.
Okay. Yeah. Thank you. Thank you so much.
Thank you, Theo. We have one more question.
Yeah, thank you for the presentation. I enjoyed a lot. This is Channing Dan. I was curious, you mentioned this non-conforming finite element method. So in general, there's a large number of non-conforming finite element methods. So I was curious, what is exactly this non-conforming here? What's the method that you used here?
Yes, let me go back. Oops, sorry about that. I will have to quickly go there.
No worries, or you can just tell me the name, because
here there is continuity of specific quantities along the edges of the triangle, but the resulting shape functions denoted here as n1 up to n9 create approximations that do not form subsets of functions with square Lebesgue integrable second derivative in the two-dimensional plane. Their first derivative, so I'm talking about the derivative of the shape function in the global setting of approximation. The first derivative has a squared Lebesgue integrable measure.
Yeah, so this method is quite outdated, I think. There's lots of like non-conforming method like HO, hybrid high order, or HDG developed from the University of Minnesota. Yeah, maybe that's something that
There are several.
For example, you mentioned about the robustness of finite element method, the continuous version. Actually, like if you look into the HHO version, the robustness has been proved to be as robust as the continuous version, even for the interface program. So yeah, this is just some comment.
Correct, but please note here that we have also the velocity potential equation, yes, which is approximated by a linear triangle. So in the overall asymptotic convergence rate, there is no point in going higher because everything will be in H2 in the eigenfrequencies. So the order of approximation of the linear triangle.
Yeah, I can tell you that HHO can go to even constant P0 constants, not even like P1. But anyway, thank you very much. It's a very nice talk. Thanks.
Thank you, Theo.
May I stop sharing my screen?
Yeah, just it's Mike Malin here. Thanks a lot for the talk. Yeah, it was nice that you came. It's nice to see your face as well, because I know we haven't been able to catch up in the last few years because of COVID, but hopefully we'll see you in the UK. But we've got to go and have a conference dinner here.
Okay,
it's time for beer in Australia.
I know it's about 7 in the morning now in the UK, but it was very nice seeing everyone. Thank you again for the wonderful workshop, and Mike, whenever you visit UK, please let me know. Looking forward to meeting you in person.
Thank you very much, Theo. Let's thank Theo and all our speakers for this afternoon.